Hello again, class. Welcome back to the last recording of this chapter on frequency response. Like I promised, we are going to look at examples and problems related to items topics 9.2 and 9.3. 9.2 is internal capacitive effects. That means for the MOSFET device and the BJT device, what internal capacitances exist within the devices which influence high frequency response. The next topic, 9.3, are for these same devices, once they are put into simple amplifier circuits like a CS common source circuit or a CE common emitter circuit for a BJT, then how do we go about finding the high frequency response? Okay, so those are the topics that we will look at the problems for. Okay, all right, let me move this out of the way. And this was the theory slide on MOSFET. The next slide, slide 33, 34, 35, 36. Okay, so we stop at slide 37, and there are two exercises. So there's not an example on this material in the textbook, but there is an exercise. And so exercises, the answers are available so we can check our work. All right, so the first exercise we look at is 9.3, and it says for an n-channel MOSFET with TOX is given 10 nanometers, length, width, LOV, the overlap length, then the CSBO, CDBO or DB0, 10 femtofarads, the VO, the barrier voltage or the natural voltage, VSB, the reverse source to body voltage is given, and V, drain to source, is given. So given all this, calculate the following capacitances when the transistor is operating in saturation. Remember, the formulas are different for when they are in triode and when they are in saturation and they are cut off, right? So it helps that it's given that these are in saturation. Hence, find all these: COX, COV, CGS, CGD, CSB, CDB. Okay. All right. So the formulas for all of this, I have gathered them at the bottom here. And I guess the COX equals epsilon OX by TOX. We have seen this before, but in case you don't remember it, here's the formula. And epsilon also has a value. Yeah, here. Epsilon OX is given, farads per meter. The rest of them, we just studied about these. COV is the overhang capacitance, and then we have CGS, CGD, CSB, CDB. Okay, CGS has this formula in saturation. CGD is nothing but COV, CSB, CDB. And the one thing to remember is this voltage VDB is calculated as VDS plus VSB. VDS plus VSB, both are given. Now why they can't directly give us VDB, I don't know, but that's how the problem is. Then that's 9.3. 9.4 says find the unity gain frequency, FT. Okay. Now remember, this is not the cutoff frequency. It's just the frequency at which the short circuit gain, also called HFE in some textbooks, HFE is also the short circuit current gain, output current by input current. So that unity gain frequency is given by this formula, Ft equals Gm by 2 pi into these two capacitances, and Gm you can calculate using this method, this formula. Okay, so those are the two exercises 9.3 and 9.4, and here are the answers. So starting with COX, which is this ratio of epsilon OX by TOX, which comes out to be 3.45 into 10 to the power minus 3 farads per meter square. And generally, we want to convert this to farads per micrometer square, because everything else is given in micrometers, other lengths like this length, for example. So remember, COX, we always use it in our formulas, including this formula, like ID formula. It is per micrometer square. So make sure you remember that one step. If you forget that, you're going to mess up the answer. So to convert from farads per meter square into farads per micrometer square, you have to multiply with this term. First you convert meters to micrometers, right? And then you have to square it. So that is one step to remember, COX. COV is this formula. So it comes out to be 1.72 femtofarads. CGS is this formula plus COV. CGS, let's see. Yeah, it consists of two items, right? So maybe I should say plus COV. And take that out, but you can see it in here. CGS is this plus COV that we calculated above, so that adds up to this. CGD is nothing but COV. CSB is this formula. As VSB is given, VO is V0 is given, everything is given here. For CDB, like I said, this VDB is the sum of two things, 2 plus 1. Then you calculate, you get that to be 4.5. So notice that all these answers are in femto, right? So that's 10 to the power minus 15. Remember that. GM is this formula. We are given Kn square, Kn prime. Then we have W by L. Now Kn, I don't know if I showed where to calculate Kn prime. Sorry, I didn't. So let me tell you what this is. This is mu n into COX, right? You remember the formula for Kn prime. So mu n, oh, I've given it here. Kn prime is 160. If you didn't have it, then you can still find it as COX into mu n. And you have to look up mu n, which is a constant. But it's given here, so that's good. W by L, which is 10 by L. L is given too, right? L is 1. So that should be 10 by 1. I'm sorry, yeah. Times ID. ID is 100 microamps, so that's given. So GM, you have all the values, and this is 1 again at the bottom. So that's 0.566 milliamps per volt. From there, you can find the unity gain formula frequency using this formula. So Gm by 2 pi into these two capacitances, which are each in femto. So if you did that, you get 3.4 gigahertz as the answer. Okay. So this is a straightforward application of all the formulas that we have used related to there you go. So that completes all the necessary formulas to solve this exercise, right? Yeah. Okay. So I'm going to move on to the next example or numerical, which is a problem from the back. So remember, so far we are only working on using the formulas for the various capacitances, right? So first we did an exercise for MOSFET. Now we are looking at a problem for MOSFET. It's the same thing, not too much different, I think. So refer to the MOSFET high frequency model shown here. Evaluate the model parameters for an NMOS transistor operating at ID is given, VSB is given, VDS is given, and a whole bunch of other things are given. When they say model parameters, all these items here have to be found. So the four capacitances 1, 2, 3, 4, GM, RO, yeah, VGS, VBS, and so on, right? Right. Okay. So again, here's the collection of formulas starting with COX, Kn prime. Yeah, here Kn prime, we just have mu n and COX. If you multiply the two, you get Kn prime. You use that in this formula. Something is missing here, so we use this formula to find the missing item. Maybe we use it to find VOV. Then we need GM because GM appears here. So GM 2ID by VOV. GMB is a new term I told you that appears here. It's the product of, is this gamma or sigma? Something like that, this X times GM, where that is given by sigma by this formula. And then RO is just the output resistance, the intrinsic output resistance, which you can use one of these formulas. I think this lambda is given, so we use this formula. Okay. This is a little complicated to find this business. For that, we are given 2 phi f. So you plug that in and you can get the answer. This gamma is given 2.5 v to the power of half. I think that's what this means. Isn't that interesting? Yeah, that's an interesting constant. Okay, so let's see how to do problem 916. Here it is. So starting with COX, again you have it in farads per meter square, and we want to convert that into farads per micrometer square. So if you do that, it comes out to be 4.3 femtofarads per micro. So the only thing you have to do is to multiply by this. Multiply the answer you got here by 10 raised to minus 6. That gives you the micro, but it's a square, so you got to square it. Kn prime comes out to be this. 193 microamps per volt square. ID is given as 200 microamps. So we can figure out VOV as 0.31 by substituting in this formula. Once we know VOV, GM is 2ID by VOV, which comes out to be 1.3 milliamps per volt. RO is 100K using this formula. And then this X, I must find out what this is sigma by this formula. So that comes out to be 0.19. So you've got all these parameters now. Next, what we need are these capacitances. So for CGX, here's the formula, and you get 61.6. CGD, this is the formula, just this portion, which is 4.3. These junction capacitances, they depend on the bias voltage, the reverse bias voltage. So that's, and this CSBO and CDBO, or CSB0 and CDB0, these are given to be equal in this case. So then you apply the formula and you get these. Finally, FT is this formula. So these are all a straightforward application of the formulas, and I think I'll give you one problem, the small one, the 4 marks one in the final exam on this material that we cover in frequency response. So it won't be a big problem, not a 20 marks problem, but just a smaller one, the 4 marks. So be sure you are familiar, and again I promise to only give you from the MOSFET formulas, not the BJT. So at least make sure you understand and you're comfortable doing these kind of calculations using these formulas for capacitance of MOSFET devices, both on the low frequency and the high frequency. That's my advice to you from an exam point of view. Okay, so various new things have shown up here, like this parameter, this formula, for example. So unless you do at least a little bit of practice and all these formulas, unless you do a little bit of practice, you're likely to struggle in the exam. Okay, so get some practice. Oh, I wanted to say that you can see now that the FT is a high frequency, right? Gigahertz. So when you study high frequency response, most of the answers we'll get for frequency will be in the mega and gigahertz. Okay, so that takes care of that problem, problem 9.16. Now we move to BJTs. We are still on topic 9.2. We are still concerned only about the internal capacitances. Previously we looked at MOSFETs. Now let's look at BJTs. So for BJTs also, I introduced you to these formulas. There are 2 or 3 capacitances that we are concerned about. They're called C pi and C mu. C pi is the sum of 2 other things, CDE, CJE. They have their formulas here. This new constant tau p has been introduced. And then we have some voltages here. And then we again have the FT, which is the unity gain frequency. So all these are summarized here on this table. The next slide. Now slide 40. This is 41. And here are all the formulas. There is this additional resistor that was introduced, right? I told you that's between this B and B bar or B prime. And so we look at a problem or two using all those formulas and those constants. Oh, there's an m that we were introduced, right? mCbj. That m is here in the numerator, and sometimes it's just called m, sometimes they put this mCbj on it. Okay, so exercise 9.5. Find these four different capacitors, and the unity gain frequency for a BJT operating at a DC collector current IC of 1 milliamp and a CBJ reverse bias of 2 volts. That means the collector to body has a reverse bias of 2 volts. The device has this tau f of 20 picoseconds, CJE 0 of 20 femtofarads, CPi 0 of 20 femtofarads, VOE 0.9 volts, the natural voltage, VOC is 0.5, and this M is 0.33. So again, the formulas are here. CDE, GM, because you need GM here. And CDE also is a product of two things. And of course, so you need GM. CJE is easy. C pi is the sum of the two. C mu has this formula. Okay. So this is the collection of formulas required. So I will look at 9.5 in my PDF. By the way, the PDF is called Chapter 9 Frequency Response Class Problems Part B. Okay. So exercise 9.5, CDE is the product of two things. This is given. GM is the ratio of IC and VT for a BJT. So that's 40. So you take the product of these two, you get CDE is 0.8 picofarads. CJE is twice of CJE is 0. So that's 20 times 2. C pi is the sum of these two, so you get 0.84 picofarads. C mu has this formula. So you take that 20 divided by the ratio of the 1 plus the ratio of some given voltages raised to the power 0.35. There's some m here. So that comes out to be 12 femtofarads. From here you can find Ft as this ratio, and that is 7.47 gigahertz. Okay. So again, we are speaking gigahertz. And one thing I want you to notice is that these capacitances are not very large. They are in picofarads and femtofarads. Pico is minus 12, right? 10 to the power minus 12. Femto is 10 to the power minus 15. So very low values, no doubt, but they exist. Okay, so that was an exercise, and I think these answers match. You can check it yourself. Problem 923 is the next problem, also on BJTs. So an NPN transistor is operated at IC equals 1 milliamp, VCB 2 volts. All these values are given. Sketch the complete hybrid model and specify the values of all its components. Also find Ft. The Rx is given in this case to be 100. Okay, so it's pretty much similar to this, right? Yeah, so that's why I didn't show all the formulas, but we can go straight to looking at the solution 923. Rx is given as 100. GM is the ratio of IC to VT for a BJT. R pi, which is required, this value is VA by EC. And all these formulas are actually also here. Many of these formulas we have seen before, but they also show up in this summary table 9.2. So you can look at that too. A rho is given. Now CDE is again the product of a tau and GM. tau is given, gm we just found here. So you multiply that by, you get 1.2 picofarads. CJE0 is given. So CJE is twice of this, which is 40. C pi is the sum of these two things, so that's 1.24. C mu, use this formula, and m is given in this case to be 0.5. So you come up with this 15.7. Ft is the ratio of these two. So if you do that, you got it as 5.1 gigahertz. Okay. So nothing new, it's just a repetition of the previous exercise. But I thought if we did a couple of these, we'll get some good practice on dealing with these formulas and some funny new constants such as tau f and all that. Okay, so with that we finish 9.2. Now we move on to 9.3. Here we are dealing with real amplifiers, simple amplifiers, just one BJT or MOSFET. Again, we are not looking at cascode and all that, or current source loads. All that is in the chapter 9, but we just don't have time to do it because you guys have a shorter semester. But at least if you learned the basics of the CSCE amplifiers, I think that's good enough. That's better than nothing, right? Alright, so you remember all these formulas to find the midband gain and the high frequency gain and the cutoff frequency. The cutoff frequency depends on R and C. R is not just one R, but it's the parallel combination of many things. Similarly, C is not one C, it's the parallel combination of a few capacitances. And then there is this C equivalent, which uses this Miller multiplier to complete the formula. And remember, on the high frequency side, this tells us that these are low pass filters. That means anything frequencies lower than the cutoff frequency are allowed. Frequencies higher than the cutoff frequencies get cut off. Okay, so here there are examples in the textbook both for the MOSFET and for the BJT. So first we look at the example and then maybe I'll show you a problem from the back. So example 9.3, which is on page 716, is a simple application of these formulas to help you find the midband gain AM and the upper 3 dB frequency FH of a common source MOSFET amplifier fed with a signal source having an internal resistance R signal of 100K. The amplifier has RG, the biasing resistors at the gate. The drain resistor equals the load resistor is 15K, GM is given, RO is given, CGS is given, CGD is given. So lots of stuff is given and we just have to plug everything into making a simple solution for this example. So this example, I hope I don't have to go through it too much. You can read it for yourself. So on page 716, I'm looking at the problem solution. AM, it comes out as minus 7 volts per volt using the formula shown below. And I don't think I need to talk about this. It's a very straightforward calculation. Similarly, the equivalent capacitance CEQ is found using a formula. Then C in is CGS plus CEQ. Then the upper 3 dB frequency FH is found using the formula shown there. And I think there's nothing more to discuss. Yeah, you get 382 kilohertz. So not very high. It's only 382 kilohertz, not gigahertz or megahertz for FH. Okay, so not much more to be done there. Let's move on to a problem also related to the same thing. Again, straight applications of the formulas. Yeah, a discrete MOSFET CS amplifier has this RG, GM, RO, RD. Oh, there is a load resistor 20K. Source has an internal resistance Rsig of 500K. CGS is given, CGD is given. Absolutely straightforward, easy, I think. Let's see if that's how it went. AM is this formula, RL is this formula. So you apply the parallel combination of three resistors, you get this 9.1 as RL prime. AM is minus 36.4. Part B, FH is 1 by 2 pi C in or sigma prime. C in is CGS plus this. This is the Miller multiplier. So that comes out to be 3 plus 0.5 into this, which is 26.25 picofarads. R sigma prime is R sigma in parallel with the gate biasing resistor. So that comes out to be 400K. So you plug everything into FH and you get 15.2 kilohertz. So somehow what we are noticing is the high frequency response is not going too high. For some reason the cutoff frequencies are in kilohertz and not necessarily mega or giga. But I hope you were able to follow the simple steps behind the application of these formulas to find the midband gain and the high 3 dB frequency, the high cutoff frequency. Okay, the very last topic then for problems is a CE common emitter BJT amplifier. And again I have two numericals. One of them is an example 9.4 from page 719, and a problem 939, and that's it. All right, so 9.4 from page 719. It's required to find the midband gain and the upper 3 dB frequency FH of the common emitter amplifier for the following case. A whole bunch of data is given. I is given 1 milliamps, RB, RC, R sigma, RL. The formulas are a little more complicated always for BJTs because there's extra parameters to worry about. R pi, Rx and all that stuff. But here's the formula. Now, one interesting thing in this problem is, in this example, he's given us Ft. In the previous MOSFET example, the Ft wasn't given. So I think what's happening here is, instead of giving C mu and C pi, he's given us Ft and C mu, and he wants us to find C pi ourselves. Then once we have that C pi, you can get C in as this formula. And R sigma, or signal prime, is of course this, right? So the little trick here is to use this formula to get C pi. So I think other than that, there is not much complicated about this example. You can look at it yourself, page 719. He starts off by finding GM, R pi, R O. Then he finds C pi. C mu is given. So you can see how he finds C pi to be 7 picofarads. So he plugs everything in and he gets a mid voltage or mid band gain of minus 39 volts per volt, which in log terms is 32 dB. Then the next step he finds FH. To do that he needs C in, which is coming out to be 128 picofarads. Then R sigma signal prime 1.65 kilo ohms. He plugs everything in and he comes up with 754 kilohertz as the 3 dB or high cutoff frequency, 754 kilohertz. Okay. We have one more problem here from the back, 939. So here again, I was going to say, if you have an FT of 800 megahertz and the answer for FH is only 754 kilohertz. So you can see that the actual 3 dB is much lower than the FT. So that's something there to remember. All right, problem 939, a particular BJT operating at 2 milliamps is specified to have an FT of 2 gigahertz. C mu is given. Again, C pi is not given here. Rx is given, beta is given. The device is used in a C amplifier operating from a very low resistance voltage source. So here all signal is 0. So that simplifies all these formulas. Because once it's 0, you can eliminate that term, right? If the midband gain obtained is minus 10 volts per volt, what is the value of FH? So that's kind of interesting. So he gives us some parameters, many are missing, but he gives us the midband gain. And this makes it convenient. R signal equals 0. So we can find some of the missing stuff and then put that into the formula for f of h, the high cutoff frequency, and find it. Part B again, if the midband gain is minus 1 instead of minus 10, then what FH is obtained. Okay. All right. So the formulas are all here. Nothing new here. Let's look at the solution. 939. I think this should be 939. I picked it from the other edition, the 10th edition. That's why I put that number. Anyway, so this is FH, Cn, all the formulas are here. So we need to find C pi, R pi, GM, etc., right? So that we can then find FH. That's why we need to find all these other things. So GM is like this, R pi is this, AM is given, and the formula simplifies to this from here. So I show you both. If R signal is 0, then these terms go away. So this big formula and this term also goes away. So the formula is much simpler. Am is just R pi by R pi plus G Rx into this. So using that formula, we can come up with the value for RL prime as this. Similarly, C pi plus Cu is this ratio, and this Ft is given. So C pi is this minus Cu, C mu, which is 5.37. Cn then becomes C pi plus the multiplier times C mu, the Miller multiplier, which is 17 picofarads. Finally, we need to find our signal prime, which is this. Normally, our signal prime would be this formula, right? But because our signal is gone, 0, we only have to worry about the other two terms, right? So that's what you see. Our signal becomes just this. You plug all that into FH and the formula, and you get 99.2 megahertz. Now the value is nice. It's in the megahertz, not just the kilohertz. Okay, there's a part B. If the magnitude of AM is reduced to 1, then what happens? So you go through the calculations. FH now is 227.6 megahertz. So we went from 100 megahertz to twice that. Now AM was reduced because RL prime is reduced, right? By reducing RL prime from whatever was the previous value, I think here it was about 10. Yeah, this value. Yeah, oh, sorry. It was 0.133 kilo ohms. Here it's... Anyway, what he did was change RL prime. We didn't calculate that separately. But because of that, we get a different cutoff frequency. Okay, that's it. So that was the application of these formulas for BJTs. Now again, I told you I'm not going to give you any problems on BJTs in the exam, so you don't have to spend your time on this unless you really like the topic and you want to also become familiar with BJT material. But definitely there will be a simpler problem in the exam on MOSFET frequency response, either low or high, using these formulas, etc. Okay, with that we come to the end of this lecture, and good luck with your quizzes and final exams. Thank you.